Let's look at how to design a V-belt drive. And design means we're going to pick out the sizes. Before you can do that, you need to know some things, like what kind of machinery do you have, what kind of motor do you have, and what speeds do you need. We'll see why as we go along. Let's practice on this example. Let's say we have a fan, big fan. It's got a 10 horsepower motor, 1800 RPM, and it's going to run 18 hours a day. The motor is 1800 RPM. We want the fan to turn 1120 RPM. And we're going to start out with a center distance of 20 inches. So from the center of one sheave to the center of the other is 20 inches. We might have to adjust that later on, and that's okay. We can do that because we're the designers. To adjust that, we might have to modify where we locate our motor mount, for example. All right, here we go. So we've got a fan, and we need to find the design horsepower. This fan has some operating conditions, and even though it's a 10 horsepower motor, we might need to pick out belts as if it were a bigger motor. So first, we'll find the service factor. And this is a table out of our book. You can get these tables from equipment manufacturers, belt drive suppliers. So here's the one we're using. We look through here and we see, can we find fans? Yes, there it is. There's fans up to 10 horsepower. Now, we're operating 18 hours a day. So which one of these three columns do we need? We're 18 hours a day, so we're over here. So that means we have a service factor of 1.2. That's what we multiply times our motor horsepower. We have a 10 horsepower motor, but a 1.2 service factor. 10 times 1.2 is 12. So we are going to have to select V-belts and sheaves as if we were running a 12 horsepower motor. Now let's decide what size of belt we need. We'll use this chart. And first we'll look for the motor RPM. That's the faster one. We have an 1800 RPM motor. It's right about there. We have a design horsepower of 12. It's right about there. And those two things intersect in this area of the chart, which appears to be the A area. So we need an A belt. In other words, we need the smallest, least expensive belt. We don't need a big thing. So we're going to be able to use an A. Now in this chart, we need to find what is the minimum diameter we can use on our smallest sheave. We can't just go really, really tiny. We could not use a 1-inch diameter sheave. That would not work. So there's some minimum size based on what our motor speed is and our horsepower. Notice that 1800 RPM is not one of the choices. That's because motors are not actually 100% efficient. They're a little bit less than 100. So if your motor says that it's 1800 RPM, its actual speed is closer to 1750, so we'll use that. Then we have a 10 horsepower motor, and in this table it does not say design horsepower, it just says motor horsepower, so we'll use that. Okie dokie. According to this chart, we cannot use a sheave that is smaller than 3 3/4 of an inch diameter. And by the way, that's not the outside diameter, that's the pitch diameter. So in that way, it's just like with gears, it's the pitch diameter that we're thinking about. Now let's figure out the speed ratio. Sound familiar? We did this with gears. So the fast speed divided by the slow speed. 1750 divided by 1120. Our speed ratio is going to be 1.56. Or we could look it up in the table. Here's our belt drive table. This is out of our book. And here's what to do. Over here in the middle of this chart, the manufacturer gives some two motor speeds, 3600 or 1800, which will actually be 3500 or 1750 RPM. So we're going to use the 1750 RPM because that's our motor. And we want the slower speed to be 1120. Well, in this chart, the manufacturer is telling us if you use 1120, well, 1122, you'll have a speed ratio of 1.56, which is what we just figured out. And this is not exactly 1120, it's 1122, but 2 RPMs difference is negligible, so this will be just fine. So this is the range that we'll be looking at. Now, in this range of stuff, in this speed ratio range, some of these are for A belts. Some are for other sizes of belts. We don't want those. We want A belts. So we'll just look for what combination of sheave, here's sheave combination, gives us this speed ratio. But we can't use those two. They're too small. We figured out that we need at least 3 3/4. So we could use any of these others. Let's use this combination just for the heck of it. This chart here is from the book, as I mentioned. Let me show you. I gave you a handout, a PDF, that has the full chart stretching all the way across from side to side. In the book, he puts the right half on one page and the left half on the other page. So here's the right half, here's the left half of the chart. So there's we're going to use this sheave combination. Here's the right half of the chart, and they list the sheaves over here again. And we want to find one of these belts that has a center distance that's closest to the one we want. So here are the belt numbers. 58 means the belt is about 58 inches long, 67 is about 67 inches long, and so forth. And each of those belts has a center distance listed next to it. Well, this belt right here, the A58, has a center distance of 19.9. That's pretty close to our original center distance. We're starting with an ideal of 20 inches. These other belts are not going to work because their center distances are even longer. But this one, A58, that's pretty close. So we'll use that one, and in our design, we'll just adjust our center distance to be 19.9. Now, let's figure out how many horsepower per belt we are going to be able to pull, because we want to find out how many belts do we need. So here's our sheave combination. Here in our motor speed, it lists horsepower per belt. Okay, we have a capacity of 4.26 horsepower for each belt. But there's a correction factor. And here in this chart, they are saying F stands for factor. That's the arc length correction factor. So here's our belt, A58. There's our new center distance. Here's the correction factor. What is that about? we are going to multiply the horsepower per belt times the correction factor we just found, and we come up with a new horsepower per belt. We can actually only pull 4 4/1000ths of a horsepower per belt. Why? If you had two sheaves that were the same size, your belt would be wrapping all the way around a full half of each sheave. So that's a good distance of wrap. But if one sheave is much smaller than the other one, look what happens to the angle of the belt. And look at what that does to how much belt wrap you get. If one sheave is much smaller than the other, you don't have as much belt length grabbing that groove in there and keeping things turning. So you can actually, your capacity for turning this thing is less if you have a little tiny sheave. So that factor we looked up was related to what is the relative distance between them and size difference, and each one of those combos gets a factor. So we had to reduce our actual horsepower per belt by some factor because we don't have 180 degrees of belt wrap in our combination. Okay, now let's figure out how many belts we need. We just looked up the horsepower per belt and a correction factor. So now let's figure out how many belts that means. What was our design horsepower? We had a design horsepower of 12. Remember, it's a 10 horsepower motor, but we had a 1.2 service factor, so we are designing our belt drive as if it were a bigger motor, as if it were a 12 horsepower motor. And we just figured out that we have a capacity of 4.004 horsepower per belt. So obviously we'll need more than one belt to be able to pull 12 horsepower. How many belts will we need? We'll say design horsepower divided by that actual horsepower per belt that we just found. We get 2.997. Well, we can't have 2.997 belts. We could have 2 belts, or we could have 3 belts. Would 2 belts be enough? No, it would not. We need more than 2 belts. So we're going to need 3 belts. Even though I know this is close to 3, but it's not 3, and so we need 3 belts. Can I just say, if you find yourself with a belt drive where it tells you only need 1 belt, it's good practice to specify 2 belts anyway, and here's the reason. If you're out on the job site, or your customer is out on the job site, and a belt breaks for whatever reason, if you've only given them 1 belt, when the belt breaks, that's it. They're shut down until somebody goes somewhere and gets a new belt. But if you have given them a 2-groove sheave with 2 belts, if 1 belt breaks, they can limp along and keep running on the 1 belt while somebody goes and gets another set of 2 belts to install. So there you are. Let me say, well, no, I think we're running out of time, so I'll say something in our next lecture.